What page?
422 is that example. It's not hard to do, it's just not worth the time and effort right now. That's something you can do in calculus. Alright. So let's go the other direction. 3, 2. I spelled it right. Logarithmic. Logarithmic functions, or logs for short. Most people just call them logs, log graphs. They don't say the whole word. Logarithmic functions, a little review. If I have f of x is equal to, what would be a good one? The cube root of x. And g of x is equal to x cubed. Right? What happens if I compose them? Do a composition of the functions. What functions do I concentrate on first?
F of x.
You concentrate on the f function. The f looks like the cube root of. What function do you worry about next?
G of x.
And g of x looks like x cubed. What's the answer?
X.
X. Alright, if I go backwards. G f of x. G of f of x. The function I concentrate on is g, which is something cubed. The something happens to be f of x, which is the cube root of x. What's that one equal to?
X.
X. What does that tell me about those two functions?
They're equal.
Nope.
Those two
What does it tell you about f of x and g of x?
The opposite.
Close, no cigar. Opposites would be change in sign.
Reciprocals.
Not even close. That doesn't look like the reciprocal of that. Come on. When you compose two functions together backwards and forwards and you end up with just the domain, x, then those functions are called g of x is the inverse of f of x. In other words, g of x is equal to f inverse of x. Don't read that f negative 1x. That's f inverse of x. Alright, and that's one of the properties of inverse functions, is when you compose them with each other, they just spit out the domain. They just spit out the domain. Alright, so if I give you an equation, can you give me the solution?
2. What x equals to?
What's x equal?
2.
If x is equal to 2, 2 squared is?
Yeah, I mean 3.
3. So, generally, just by looking at this, you can get to 3. The math behind all that is you go 2 to the x equals 2 to the third. The one-to-one property says if your bases are exactly the same, your exponents also have to be exactly the same. So x equals 3. That's the math behind it. But your brain kind of figures it out on its own, doing that property without even thinking about it. The problem is this. What if I have 2 to the x is equal to 20? How do I solve for x? Wow, that gets a little crazy. So what's the question that you have to answer if you want to solve for x? I mean, how did you know this was 3? You ask yourself, what power do I have to raise 2 to get to 8, right? So here the question is, what power do I raise 2 to? Sounds like a dress, you know, those 2 2s. What power do I raise 2 to? And then to get, so the word 2 3 times in a row. What power do I raise 2 to get 20? Now the cool thing about functions in essence is they're always asking questions. If I take the square root of 4, what do I get? That's a function, square root of x. If I take a number and I square it, what do I get? Well, that's also a function. If I do 4 squared, that's a function. So this has to be some kind of function, because it's going to take a value and spit out an answer. What power? So it's going to take the 20 and then it's going to spit out what power. So if I can find the function that actually answers this question, it would be really great. Because if I do, let's say f of x is equal to 2 to the x. And I know that f inverse exists. And I know it exists because 2 to the x is a one-to-one function. It's constantly growing, constantly increasing over time, so as x increases. So if f inverse exists, then I can apply it and actually use it. It's kind of like if you have x squared is equal to 9, you can square root both sides of the equation because they're kind of inverses. So what I'm going to do is I'm going to take this equation, I'm going to apply f inverse to both sides. Alright, say it again. I guess if we had the graph of the inverse function, solving that equation 2 to the x equals 20 would actually be kind of easy. So, here's the graph. If you can graph the original function, 2 to the x, which goes through 0, 1, hugs the negative x-axis, hits 0, 1, and shoots off to infinity, you should also be able to graph its inverse. Okay? So if I'm going to graph its inverse, I need a few points. 0, 1 is not good enough. So I generally try to cheat and take a few points. So what would be a good coordinate for that one right there? Just make one up.
2, 0. I mean 2.
Negative 2 and a little bit off 0, let's say 0.1. It's a little high, barely off the x-axis. And then pick a good point for this one up here.
3, 5.
3, 5, that's decent. Remember what you do for inverse functions. You take each one of those coordinates and put it. So we're going to plot the important one, which is going to be 1, 0. That'll be right about here. So there's 1, 0. We're going to plot negative 2.1's flip, which would be 0.1, negative 2. So 0.1, negative 2, someplace down here. And then we're going to plot, instead of 3, 5, we're going to plot 5, 3. So there'll be 5 to the right and 3 up. And it's going to hug this axis as it goes down, so the y-axis now becomes a vertical asymptote, negative y-axis. It's going to hit 1, 0, but then instead of exponential growth, we're going to get this very small growth going in that direction. So this graph here is the inverse of 2 to the x. So if I wanted to solve that equation, when does 2 to the x equal 20, I would go out 20 units on this thing and find out how high it is, the height, and it'll be somewhere between 4 and 5 units tall. So this is what the graph of the inverse of 2 to the x is going to look like. Kind of cool. Hugs the negative y-axis, hits 1, 0, and then slowly grows. It's going to just, where this one is exponential growth, you flip it, it's going to slowly grow. All right, so let's give this function a name at least, so we can get comfortable with it. So we're going to call the inverse function this. Give it a fancy name. It's called the logarithm function. And this thing here literally is asking what power on 2 to get x. Whoops. power do you have to raise 2 to get to x? Alright. So, let's see here. We've actually already answered this one. This one is asking, what power do you raise 2 to get to an answer of 8? What's the answer to this? 3.
Isn't this done in another, like, algebra 2?
Possibly. Possibly.
Because
Or advanced function, probably. I always forget what's in algebra 2. So, what's this one equal to?
2.
2. Then I know the trick ones that go.
Negative 2.
Ah, wow. You know your negative exponents. I was trying to trip you up. Ah.
This comes in 3.
Dang it. Alright, fine. You know your log pretty well. Okay. I could do it later, but I'm going to do it now. Why not? Instead of talking, we talked a little bit about the graphing, but let me talk about the important functions. Now, when we talk about log, this notation, you have to read it right. This is log, this is called the base. This is the exponent. If you can keep those two things straight, working with logarithms is really easy. As long as you always recognize what the base is and what the exponent is. They're separated in this case. Where exponential functions are next to each other, logarithm functions are separated. Because it's an inverse function, you're undoing what was done. So when we talk about important bases, the two important bases are this. Log base 10, because our number system is based on 10. And the other one is log base e. That nice natural number thing. Now, when we work with log base 10, it's understood that 10 is our natural base. Not the natural number base, but it's our natural base. We're just going to write log of x. So if you see just log with no base number written, and you don't know what it is, write 10, because it's always going to be 10. So if you want to go backwards, it's perfectly fine. If you see log of x, write log base 10 of x. That way you can see what the base is. If it's log base e of x, then the notation becomes ln of x, which is called the natural logarithm. Or the natural log, because it has that natural number in it, e. So log by itself, base 10, ln base e. ln base e. Those are the two important bases. And then the one thing that will save you for the entire chapter, it'll actually solve 90% of the problems I'm going to throw at you. So star, important, convert between a exponential and a log. The cool thing about these functions is it's really easy to rewrite it in its inverse form. For instance, if I have 2 to the x plus 5 is equal to y. 2 to the x plus 5 is equal to y. Some weird stuff. I can convert that into its logarithmic form by just writing log. So that's telling me I'm taking out an exponential form and putting it into log form. What's the base?
X plus 5.
What's the base?
Y.
What's the base?
2.
2. 2 is the base of the exponential function. So that goes here, 2, written small and low below the log. What's the answer?
X plus 5.
What's the answer? What's x plus 5 called? It's in that position. What's it called?
Power.
A power or an exponent. That's definitely not the answer. The answer is
Oh, wow.
it's y. And with logarithms, the base is here and the power is over here. So the power is x plus 5. If you can do this conversion every time, life is easy. Because everything can be proved that way with logarithms, for the most part. Alright, what if we had ln of x minus 3 is equal to z squared? And I want to change it into its exponential form. It's already in logarithmic form. So when you're changing into exponential form, your first question should always be, what is the base? So what is the base?
Z.
Where's the base go in the logarithm? You know, this is log base 2. This is log base 3, log base 9, log base a half. So log base,
H.
go back up here. When you see ln of x, what's its base?
E.
E. So when you see ln of x, you're going to write the base is e. What's the power? Where's the power in this expression?
2.
That's the power on z, but what's the power in this expression?
1.
Ah, listen very well. When you say log base 2 of 8 and your answer is 3, what does the 3 represent? The exponent. When you say log base 3 of 9 is equal to 2, what does the 2 represent? The exponent. What's the exponent here?
Z.
Just z?
Z squared.
Z squared is whatever's on the other side of the equation. So here you have to put z squared is equal to what's left over?
X minus 3.
X minus 3. One more. Have room? I have room. If I do 10 is equal to 4 raised to the x plus 5. What am I trying to convert it into first? What form is it in right now? What's that called?
Logarithmic.
Do you see a log in here?
Mm-hmm.
No. So what form is this? It's not logarithmic. It must be the other one, which is
Exponential.
exponential. So when you have an exponential function, you want to change it to a log. So the first thing you do is you write log over here. And then you ask yourself, what's the base? So it always comes back to, what is the base of that thing? Whether it's logarithmic or exponential, you have to say, what's the base? The base is 4. What's the power? I'm sorry. Not the power. The power doesn't go there. What goes there? Oh, the answer. What's the answer?
10.
10. What's the power?
X plus 5.
X plus 5. Very important that you can figure out going back and forth between these two formats and being able to recognize exponential form and logarithmic form. And especially recognize what is the base, because that's everything. Get rid of all that. That's messy, but alright, what else is there?
So what page is this?
Oh, in the book, 427 on.
So you skipping chapters?
Not anymore. I just skipped the one right now. Alright. Alright, so let's go back to graphing. The most important thing about graphing logs and exponential functions is to find their domain and their ranges. So you can kind of get a sense of what you can plug in and what they're going to spit out. So we already talked about how this function looks, because it is the inverse function of 2 to the x. It's the inverse function of 2 to the x. And what it looks like is it goes through this point, 1, 0. It hugs the negative y-axis as a vertical asymptote, and it shoots off very slowly as x gets larger. So it has this kind of shape to it. So when we look at this thing, what is the domain of this function? For what values does it work? What is the smallest x value I can plug in?
Smallest x value would be
Negative infinity?
Mm.
You think it's negative infinity?
greater than 1. I mean greater than 0.
Greater than 0, definitely. So that would be parentheses 0. What's the largest x value you can obtain? Infinity. So the domain says you have to take the logs of positive numbers. It's the only thing that's going to work. So log of negative 2 doesn't exist because negative 2 is over here and there is no graph over here. So the best way to, for me personally, the best way to remember what the heck the domain of logarithm is to look at the graph. It tells you some other interesting things. If you take the log of a number smaller than 1 but bigger than 0, if you take the log of a number smaller than 1, bigger than 0, your answer is always going to be negative. So the log of 0.1 is going to give you a negative number, guaranteed without a doubt. The log of anything bigger than 1 is going to give you a positive answer. It also tells you that the log of 1 is... Oh, stop that. The log of 1 is 0. That's how you read coordinates. So one of the properties you have to remember is log base anything of 1 is guaranteed to equal 0. What power do you raise b to get an answer of 1? Well, b to the 0. It's the only thing that works. Another one that you might want to know is log base b of b. Whatever the base is, the other b is going to have to be 1. The answer is just going to be 1. That was boring. So basically what that tells you is if you go out b units, or in this case 2 units, your answer, your coordinate here is going to be 2, 1. Because 2, what power do you raise 2 to get to 2 is 1. If you go out to 4, what power do you raise 4 to? 2. 8, you have to go a little further, 3. And you can see how it's slowly growing. Alright, what's the range of this function? Negative infinity to positive infinity. It goes down forever and it eventually gets up to positive, and slowly gets up to positive infinity. Very slow growing function. Alright. Well, now that we have a nice base graph, we can manipulate it. For instance, what if we had g to the x is equal to 3 plus log base 2 of x. What does that do to the function? Always come back to these transformations. What does it do to our base graph of a regular logarithm?
To the left.
Nope. Left and right has to be a number that affects the x. The x has no numbers next to it.
Okay.
So if it's outside, what does it affect?
It raises
Raises it or lowers it, but in this case raises. You guaranteed need those reference lines. So here is it's raising up 3. This is the line y equals 3. So the graph has to use that reference line and the general shape of the logarithm. So if you take this graph and you move it up 3 units, this point, the important part of it is 1 unit to the right of the origin. So the first thing you have to do is recognize where's your cross. And the cross, since you only moved the y-axis, is here. So that is where your origin originally got moved to, up 3 units. So from that cross, I have to move 1 unit to the right. And that gives me my initial point. So what is the coordinate of this point if I move it 1 unit to the right?
1, 3.
1, 3? Then the rest of the curve comes from what happens over here. It hugs the negative y-axis. The y-axis wasn't moved, so it's going to hug the y-axis. And after it hits that point, it's just going to grow really slowly. So the graph has to hug the y-axis, hit this point, and grow really slowly. So this would be the graph of 3 plus log base 2 of x. Make sense? Are you awake yet? Ooh.
Yeah, yeah.
Should have coffee before you come. Let's get a little more complex. What if we do h of x equals log base 2 of x minus 3 plus 2? What happens to this graph?
Moves it to the right.
Moves it to the right 3,
And moves it up to.
up 2. Alright, so I'm going to need an up 2 line. That would be y equals 2. And I'm going to need a right 3 line. And this would be x equals 3. And the cross is happening here. So from the cross, where do I go?
It's 1 over to the
1 over to the right. What would be the coordinate of this point?
4, 2.
4, 2, because the intersection here would be 3, 2. If you move 1 over to the right, it would be 4, 2. So that'd be 4, 2. And it would hug the negative x-axis, or y-axis, so it would be coming up the dotted line from here. It would hit this point and then slowly grow afterwards. And that would be the graph. Not that bad, right? The only problem is that I've ever seen is people get confused between the exponential graph and the logarithmic graph, because they kind of look the same. You know, the exponential function would be here. They have that same shape, even though one's concave up and the other one's concave down. They get confused with it because they forget which way the asymptote is. So it's really important that you get the 1 to the right compared to 1 up, which is exponential function, hugging the y-axis rather than hugging the x-axis for exponential function. All right. Generally, logarithms don't change from those two pictures. They move them, but it's usually facing in that direction. Very rarely do you flip a logarithm upside down, like negative log of x. And even more rarely would you flip it over the y-axis, because there's really no point to talk about logs of negative numbers. So generally, when I talk about it, it's usually that. But just in case, you know, my random generator goes crazy, let's talk about this function. Throw a few negatives in there. Now, what does the 2 do?
It brings it up to.
That's the easy one. So this is up 2. What does this negative do?
Moves it to the right.
That would be affecting the x. That would be inside. This is not inside the function. It's outside the function.
Flips it.
Flips it over what? Now you got to be careful. There's 2 flips you can
The
make.
y-axis.
Flips it over the y-axis. So when you graph negative x squared, what does it look like? You know, x squared is a parabola facing up. What would negative x squared look like?
Going down.
Going down. It flips it over the x-axis. So if your negative is on the function itself, it flips over the x-axis. If your negative is on the x itself, then it flips it over the y-axis. So the first one is going to be a flip on the x-axis. And the other negative, this one here, is a flip on the y-axis, or vertical and horizontal, vertical and order. So we got to be careful with this one. It's going to look really strange. Trust me on this one. I can't think of any applications that would use either of those flips off the top of my head. They probably do exist, but I can't think of them. So the first thing is we need to move it up 2 units. Recognize where the cross is, which is right here. And which way am I going to move my 1 point that I plot? Up, down, left, right. Which way? Now these logarithms always went 1 to the right. But this is flipping over the y-axis, so instead of going 1 to the right, we're going to have to go 1 to the left. So this is the point the graph is definitely going to go through. What's the coordinate? Oh, by the way, this is x equals 2. Oh, sorry. Y equals 2. Negative 1. Negative 1. 2. So up 2 units.
Okay.
So this would be negative 1, 2. Now that would flip it over the y-axis. To flip it over the x-axis, I have to be careful. Normally it hugs the negative y-axis, hits the point, and then slowly grows. So instead of hugging the negative axis, it's going to hug the positive side. So this thing is coming down here, has to go through this point, and the growth is going to go opposite direction, because remember it got flipped. So it's going to hug the positive y-axis. Whoops, too far. My left-handedness is getting in my way. Switch over here. And it's going to hit that point and then slowly grow as x grows more negative. And that would be the graph. And like I said, very rarely would you ever see that. Most logarithm graphs, you just worry about it growing from negative and growing as it goes positive. The increasing function.
Fried chicken, fried fish, fried
Sweet tea.
whatever. I'm gonna have to delete that now. I've got that on my recording. Fried. That's easy enough.
Alright, quick review. So if we go back to f of x is equal to 2 to the x. Do you remember what the graph looks like?
No, I totally forgot.
The main point is 1 point above the cross, in this case 0, 1. It has a horizontal asymptote as the negative x-axis, and then it increases without bound as you go to positive infinity.
So it never gets to bottom. 0. Never hits 0.
Never hits 0. So the domain of this thing is negative infinity to infinity. The range of it is 0 to infinity. Never touches 0, but it goes off to positive infinity. Alright. What we did yesterday is we designed its inverse function. Now when you read the function itself, this basically says what power do you raise 2 to get an answer of x. So if this was 8, the answer would be 3. Log base 2 of 8 is 3 because 2 to the third is 8. So that's basically all logs are. It's just undoing what was done. So if you raise 2 to the 5th power, log base 2 of 32 would be 5. So it just undoes what was done.
So like if it was 64, it would be 6.
You're making me think. Stop that. Yeah. So if you went 2 to the 6 up here is 64, down here log base 2 of 64 would be 6. So the answer of logarithms is always an exponent answer. The answer is, what is the exponent? The graph of it, if you go back into how to graph an inverse function, you just take all the coordinates and flip them. The domain becomes a range becomes a domain. So 0, 1 becomes 1, 0. It hugs the negative x-axis here, so it's going to hug the negative y-axis here. So it's going to go this way. After it hits this point, it goes infinitely growth. This one's going to grow, but very slowly. So it's going to look like this. So an exponential function has a horizontal asymptote. The logarithmic function has a vertical asymptote. Does that make sense? Yeah. So basically, literally, your x and y ideas change. All right, so that's what we basically talked about yesterday.
That's all I think yesterday.
Well, I mean, there's more to it. We talked about how log base 3 of 9 is equal to
3. No, 1, 2.
which one? You just went through 3 numbers.
2.
2. What power do you raise 3 to get 9? 3 squared equals 9. All right, if we have log base 9 of 3.
1/3.
That would be the cube root of 9.
So,
What can you do to 9 to get an answer of 3?
multiply.
Mm.
Divide it.
You have to think power. Everything is a power here. What do you do to 9 to get to 3? If I wrote an equation that said, here's 9, I want it to equal 3, without using multiplication, addition, or subtraction, how do I change a 9 into a 3? You know how, trust me.
I don't have to.
You have to know how to change a 9 into a 3. I have to do something to it, but it can't be addition, subtraction, multiplication, or division.
Raise the power.
What power?
1/3.
1/3 is a cube root of 9. Cube root of 9 is not equal to 3.
1/2.
Which would be a square root of 9. The square root of 9 is 3. So the power is a half. So the answer here is half.
Oh, I get it.
Okay. Log base 3 of 1/27th.
Let me try to base it with this. It's only 1/3.
Cube root of 3 is not 1/27th. See,
Oh, wait.
okay.
It's going to be 27.
3 to the 27th power is definitely not equal to 1/27th.
That's the 1/2. That's the 1/2.
That would be a square root of 3, but square root of 3 is not 1/27th.
That was this hard.
How about this? Ignore the 1.
Alright.
What would be the power?
3.
Alright, put the 1 back into it. What does the power have to be?
1/3.
Ah! But the cube root of 3 is not 1/27th. How do you get fractions with exponents? What do you have to do to the exponent to create a fraction?
You have to multiply it.
By?
It's reciprocal.
No. Ah. 3 raised to some power is equal to 1/27th. Okay. 3 raised to some power is equal to 1/3 cubed. You agree with that?
Yeah.
Great. 3 raised to some power is equal 3 raised to what power?
First.
But it's here. It's 3 cubed.
Yeah.
But it's 1/3 cubed. So how do I write it as 3 to some power? It's a property of exponents you forgot. If it's on the wrong side of the fraction, it's going to be
Negative.
negative. What power?
Negative.
Negative
1/3. 1/2. 1/3 cubed. 3. That's it.
It's like pulling teeth. So this is equal to -3. Think about it. If you're on this graph,
Yeah.
1/27th is between 0 and 1. So it's really small, right? The answer is going to be below the x-axis. And all these are negative.
So if it was like log of 9 and 1/2.
How about 181?
181.
1/2 ain't going to work with 9.
Oh.
One's 2s, the other one's 3s.
It'd be 2, -2. That's it?
Mhm.
Okay.
How about this one? Log base 5 of 1.
Wait, I'm trying to get 1 here. So that's 1/5.
So 5 to the 1/5 power equals 1. Remember, the answer is a power, not a number. Power.
You can't have a fraction in the power?
Sure, but 5 to the 1/5 does not equal 1. It's a 5th root of 5. It's like 1 point something something.
Negative 5.
Why would it be negative? Negative only creates fractions. Negative exponents are fractions. They're fancy fractions.
I would just be
What power do you raise 5 to get an answer of 1?
1/25.
Oh my lord. 5 raised to what power is equal to 1? You don't know?
I have no idea. You just stop and stare.
Alright. Let's see, properties, exponents, 0.
0. Oh yeah, it is 0.
Yeah.
You're right.
1, right? X is equal to 1. If x is equal to 1, this is the coordinate 1, 0. Y is equal to 0. Anything raised to the 0 power is equal to
1.
1. Oy.
See, we did this stuff last Thursday, so I got
I know.
It's been a
So
week.
5 to the 0 is equal to 1. So anything raised to the 0 is equal to
1.
1.
You can give me a whole list of these things that I'm doing now.
Worried.
Watch.
Log base 1/3 of 9.
Give me a second. Wait, let me see what this looks like on paper. 9. You do it by 9.
1/3 to the 9th power is going to equal 9. Not 1/3 times 9, 1/3 to the 9th power. You do know what that means, right?
No.
That's 1/3 times, 1/3 times, 1/3 times, 1/3 times, 1/3 times, 1/3. That's too many. That's going to be like a huge number at the bottom. And plus it's going to be a fraction.
Yeah.
This is a whole number. This is a fraction base. Not that you'd ever see this. It's just weird.
So maybe you should multiply it by
Alright, if one's a fraction and the other one's a whole number, guess what kind of exponent it's going to have?
fraction. Negative.
Negative,
That's
because
right.
one's a whole number and the other one's a reciprocal. Because you have that 1 over whatever.
Mhm.
So, if it's going to be negative, you know that already because they're not both fractions.
-2.
Pulling teeth. I'm going to fill up the whole board with weird logs. Log of 2/3 of 4/9. Log base 2/3 of 4/9. Oh, by the way, this is read as a base.
-2.
Nope.
2?
They're both fractions.
It's 2.
Small number on
It's
top, big number on the bottom.
It's 2.
The answer is just 2.
Got it.
Now, if I wrote it as 9/4,
It'd be
negative 2, because it's a reciprocal.
Got it.
Pulling a dentist. I should have became a dentist.
Give me
I could
one.
pull teeth all
We're
I
pretty
want.
good at this stuff.
So, there is a relationship here. And I've been using it in a couple cases, here and here. And the relationship is this. If you have a logarithm, you can always write it as an exponent. 3 raised to the -3 is equal to 1/27. 3 raised to the -3 is equal to 1/27. So, you can also go the other direction. If I have an exponential, I could always write it as a logarithm. Same thing here. I have this nice logarithm. I can write it as an exponential, or I can take the exponential and write it as a logarithm. It doesn't matter. They're interchangeable. So one of the most powerful things about logarithms is this. Log base b of x is equal to y. This basically reads if and only if. It's a fancy notation. If I can write it this way, I can also write it the other way, or vice versa. B raised to the power of y is equal to x. And it's not hard to remember this. You just have to remember that the base is the first thing you always look for. The power is the second thing you always look for. In an exponential, the base and power are next to each other. In a logarithm, the base and power are opposite each other. One's on the left-hand side of the equation, the other one's on the right. So, if we have log base 5 of x minus 2 is equal to y plus 5, how do I write that as an exponential?
Which one's exponential?
Exponential has a base and an exponent and an answer. So the important thing is base. Base is always first. What's the base?
Log 5.
Log is not part of the base. Log is a function.
Okay, then it's x minus 2.
No, what's the base? I've been saying it throughout this whole thing.
Really?
I said it several times. This is read log base 9 of 181.
Log base. Oh, okay, 5.
It's 5. So over here you write 5 first. Then you have to decide what's the power.
X minus 2.
But I just said, in a logarithm, the powers are opposite each other. In an exponential, they're next to each other.
So then it's y plus 5?
It's y plus 5. So you write y plus 5 up here as an exponent. And whatever's left over is what it's equal to. So that's the logarithmic form. This is the exponential form.
So how do you solve that? Or
Yeah, and we're not even talking about solving yet. Let's work with properties first to unmask some of this stuff. If I have 4 raised to the 2z plus 1 is equal to y minus 3, how do I rewrite that as a logarithm?
so it'd be 4
Well, the first thing with a logarithm, you have to write,
a log
so you go log
of 4
of 4?
log 4
How did I read this one? Log,
base 4.
okay, log base 4.
Raised y minus 3 power.
It's not a power.
Uh,
It's of y minus 3.
of y minus
And by the way, y minus 3, if you're going to give it a name, 4 is a base, 2z plus 1 is a,
so it's x.
what's it called though? Give these things names, it makes life a lot easier. 4 is the base, 2z plus 1 is called the, stop it! What? If I write 2 cubed, 2 is the base, 3 is,
Exponent.
thank you, 4 is the base, 2z plus 1 is
Exponent.
exponent. Y minus 3 is just an answer. So it's log base 4 of the answer is equal to the exponent, which is
2z plus
2z plus 1. When you're working with weird functions, it's best to know what all the pieces are. Because if you know what the pieces are, then manipulating it is much easier. When we get to trigonometry, the same thing has to happen. Functions always take a number and give you a number, right? But that's algebraic functions. You know, polynomials, we're used to that. You throw a number in and it generates a number. When you're dealing with functions, much more complex ones, like if I have this function, and I say x is the number of seats that we're selling at a concert, and this is R, which is revenue, then x is measured in number of tickets sold, and R of x is how much money I'm making on my concert. And once you get that idea of which each piece is meaning, then the word problem or whatever it is becomes much simpler to work with. But even that case is just a number and a number, right? In this case, everything has a name. You know, you have your base here, you have your exponent here, and you have its answer here. When you reverse it into a logarithm, log base 4 of the answer is equal to the exponent. And as long as you can give each piece a name, it makes life a lot easier on you. You don't trust me yet, do you?
No, I got you.
Okay. Because when we get to sine, cosine, and tangent, if you don't know the difference between which number is an angle and which number is a ratio, it gets very confusing. Because then you'll just be taking sine of anything, and it might not even be an angle. And then it makes absolutely no sense. Alright, my little soapbox for the day.
That one looks like it's about to die. Log of 1/3 b minus 2.
Change it to an exponential form.
Alright, so it'd be 1/3 b plus 3 equal with a minus 2.
Times b plus 3?
No, exponent of b plus 3.
Now, if I'm going to write it like this, would this be proper?
No, because you need the parentheses.
Yeah, you definitely need parentheses around the 1/3. Is equal to?
A minus 2.
A minus 2. Whew, all that just to get to that. So, oh, by the way, either of these graphs in the beginning can be translated up, left, right, upside down, flip over the x, flip over the y, things like that. So you just got to be really careful with two things. With an exponential, negative x-axis asymptote goes through 1 up. Logarithmic functions, y is a horizontal asymptote, 1 over to the right. Those become the important points. So from the cross, 1 up for exponentials. From the cross, 1 to the right for logarithms. And you know what the cross is, right? If I move it up and right, the cross is the intersection of those 2 dotted lines I draw. All right, so that's the quick review. And pulling teeth.
That's pretty fun stuff.
Not
I really do enjoy this class.
Oh, logarithms, I think, are one of the easier things in the world. Oh, we did talk about one other thing yesterday. Let me stick it down here. Actually, 2 other things. One is this thing. Limit just means I'm going to take a value and send it someplace. It could approach a single value like x equals 2, or it can go to infinity or negative infinity. So it just means I'm getting close to this number. It does not mean that I equal this number. Does that make sense? So if I say the limit as x approaches 2, I'm going close to 2, but I never ever get there. So it's like constantly moving. But in this case, I'm going to let x go off to infinity. Because obviously you can never ever reach infinity, because once you're there, there's always one more. So if I do this to this weird thing, and x gets really big, very, very large. So think of it. This number down here goes to 100,000, and this number up here goes to 100,000. Do you think my answer is going to be huge or small?
Probably small.
It's probably going to be small. It's a balancing act between 1 plus 0.00000000, and then raising it to an astronomical exponent. Usually when you raise things to large exponents, the number gets quite large, except if the number is smaller than 1. Then it goes quite small. So this is doing a balancing act between being small and large at the same time. The cool thing is, it equals a very specific number.
8?
E.
I thought it would equal 2.
Nope. It's close to 2. This is 2.7128. Blah, blah, blah. It's like pi. It's one of those weird irrational numbers. This is called the natural number. All right, the second thing of importance, there's a few others that I'm skipping, so you'll have to watch the video, is that if you write log base 10 of x, the shorthand for it is just remove the base. So when you write log by itself, like your calculator has log, you don't have a calculator. When you get a calculator, it'll just say log, no base. So if it has no base, the base is assumed to be 10, just like the number of fingers on your hands. And if you do log base e of x, this fancy natural number up here, we just write it ln of x. So these two buttons are on your calculator, log and ln. So if it's log base 2, we have to do something else. We have to do something else to figure it out.